want to integrate go. Can you see that okay if I just do that? Yeah. Okay. What are we going to do with this? Suggestions. There's really two ways we could go about this. And let me put something out there for you. You can do multiple substitutions, and you could make a u-substitution, and then that might simplify things a bit. And then you could do a v-substitution and simplify. I mean, you could have multiple layers of this stuff. When you're all done, you'd have to just kind of reverse the order of those substitutions and work backwards. But that's fine. As much as you can, as you get better at this stuff, probably it's easier to try to just lump those into bigger substitutions. But maybe we'll look at, this is a good example of one to look at maybe in 2 layers, and then we can look at it in 1 layer. Ideas. What's an obvious, maybe easy substitution that we get? X over 3, yeah. That's a pretty minor one though, isn't it? All we're really doing is we're just changing just the argument of those trig functions. And it's going to make things look a little simpler, but let's do that. So what if we said u equals x over 3, then what's du going to be? 1/3 dx, okay, right? And is everybody okay with that, taking that derivative in differential form? Because all you're really doing is you're saying, what's du dx? Isn't du dx equal to 1/3, and then multiplying both sides by dx? That's another way to do it, right? So we just get dx over 3, okay? And we can go ahead and execute that substitution. And what do we get then? We do that. We do that stuff. We get the integral of what? And now our job is just to go through and see if we can make a complete substitution, get rid of all the x's and end up with just u stuff instead. So what's this going to become right here, this first factor? Good. Sine of u to the 8th. And here's something else that I want you to remember. You got to always keep track of. What does that mean when I put, it's kind of shorthand notation for us. If I put an 8 up there, what does that really mean? It's the quantity, sine of x over 3 to the 8th, right? But we just write it this way so we don't have to clutter things up with so many parentheses. That's the only reason we do it. Okay. So we get sine to the 8th of u, cosine u, right? And then the dx would become what? If I solve, because all I've got there is a dx. So dx would just be what in terms of du? 3 du, okay. So I'll put the 3 out front, right? Du, okay, not bad. That helped. Looks a lot better. But we're still, that's not a standard form, is it? Right? I mean, we only have a couple standard forms for trig functions, especially for sines and cosines. So can you think of another u-substitution? And your goal is, and this takes some practice, it really does. U-substitution is not something you just get immediately. It really takes some practice. What you want to kind of train yourself to do is think of this in terms of not only a u, or now maybe a v, but also the dv, right? Because sometimes the dv, it might end up, the derivative of your whatever variable substitution you're making might end up being a big thing too. So let's do one other thing then. Let's rewrite this. This might help, and I would urge you to maybe even do this for a while until you just really get used to this process. Let's rewrite this part right here as sine u quantity to the 8th. Okay. Awesome. Okay, so what do you think now? Is that does something pop out at you there? Do you see a u substitution you can maybe make? Sine u, yeah, does that make sense? Because sine u is the what do I say, the argument of that power function, right? Sine u is what is in the parentheses, that's the quantity that's being taken to account, right? Does that make sense? And that's kind of what you're looking for with those substitutions, is you want to take the interior part of some composition of functions. Did everybody see that? That's probably not a bad choice if we were to try that. Okay, so let's do that for our v substitution. So if v equals sine u, then what's dv going to equal? Say it again. Hang on, what's the derivative? You're thinking antiderivative. What's the derivative of sine? Cosine. Cosine u du. Okay, is everybody okay with that? I want to make sure everybody's okay with that. But please ask. If you're not, ask a question. If you got a question, other people can too. That make sense? Okay. Okay, so now, what if we, now this is going to change things a lot. Now, if we make that substitution, look what happens. All of a sudden, things start to look a lot better. Now we get this 3 out front, but I've got sine u to the 8th. Well, that's just v to the 8th, and there's my dv. Aha, that looks like something we can deal with. That's just a normal power rule problem, isn't it? Right? Yeah. Okay. So what's the answer to that? Just power rule. What's the antiderivative of v to the 9th? Or v to the 8th. Whoops, I'll give it away. V to the 9th over 9. Okay, good. So we get 3 times v to the 9th over 9 plus c. And I could simplify that a little bit, right? So we could get v to the 9th if I reduce over 3 plus c. Now all we have to do is just reverse those substitutions. So if we go from v's back to u's, let's see, what was that one? Well, every v needs to become a sine u, right? And so that looks like sine u to the 9th over 3 plus c. And then if I reverse that all the way back to x's, wasn't it just x over 3? U is just x over 3. So we end up with sine, and I'll go ahead and put the 9 back in there, sine to the 9th of x over 3 plus c. Okay. Make sense? Okay. So now, oh, look how tricky this is. So we did 2 substitutions there. Our blue substitution was the U substitution, the V substitution was the red substitution. How about if we just do one purple substitution that combines them both? How about that? What could we have done? Maybe and just skipped. We made that process a little more straightforward. Sine, I'm going to go ahead and write this as a quantity. Sine of x over 3 to the 8th cosine of x over 3 dx. How could we have done one kind of double substitution there?
Just make the sine x over 3.
Sure. Yeah. Does that make sense? We could have taken everything inside that power function, the sine of x over 3, and called that u, and just done it in one step. So then, what's the derivative of that going to be by the chain rule? Derivative of sine and is, there you go. And then the derivative of x over 3, 1/3. Good, and then we need the dx, right? Okay. Okay. And so if we make that substitution, then we just end up with, that's just going to be a u to the 8th, right? And what's this going to be? Let's see, cosine of x over 3 dx. If I isolate that in terms of du's, what is that? 3. Okay, I got to multiply both sides by 3, so I get a 3 du, right? We just get there a little quicker. So there's our 3 u to the 9th over 9, right, which we found out was just gonna be we simplify that, we already did this stuff, right? That's just u to the 9th over 3 plus c, reverse that substitution, and we get there a little quicker, just one step. Okay, make sense? Okay? All right, let's try another one. You know, there's a couple that I think are just, I'm gonna pick a couple myself, because I think there's a couple that really are good ones to do. How about, and these are on the homeworks. Okay, what if you did, and this is pretty obvious, I think, but just, I want you to see what, just did that for a second. Then we want to pick a u, thinking in terms of what the du is going to be. I want you to kind of tell me, take 30 seconds and study that a little bit. Tell me what you're thinking strategically. Why are you picking this u? And also, don't feel like, I don't mean to imply here that it has to be the right choice of u on the first try. I mean, a lot of times when you get into harder calculus problems, you just try something and see if it works. If it doesn't, you try something else. So it doesn't always have to work first time. Okay, everybody agree with that? It'd be, right, okay, good, so we got, so everybody agree this might be a good choice for our u, and the thinking is, it's gonna simplify things, because then we end up with just one variable to a power on the bottom, which I could write as a negative power, right? That'd be nice. Now think of it in terms of looking ahead, what the du might look like, because you always have to try to account for that du. If I'm differentiating a cubic polynomial, what am I gonna get back from that? Okay, yeah, I'm gonna get, right, when I differentiate this, right, you can kind of see that you're gonna get back some constant times x squared, aren't you? Right, and so you can kind of get a glimpse ahead there. That matches that x squared up there too, doesn't it? Right? A mistake, and if this doesn't make total sense, don't let it bug you. But I see this a lot. You kind of peer inside the minds of people that are starting to do calculus. A mistake that people make when they're making their u substitutions is sometimes if they see stuff and like maybe an x squared on the bottom, they'll think, okay, well, if I pick 16 minus x cubed, and somewhere in that function, if I had an x squared down there, that could be my du. Well, it can't because it's on the bottom. Does that make sense? You got to think about the du is typically, like if I have a power of x like this, the du is always going to, that power is going to have to show up in the numerator, right? It doesn't matter that if your u might be in the denominator, but when you differentiate a positive power of x, you're just going to get a smaller positive power of x that, would be in the numerator. Does that make sense? So it's, I mean, that's kind of just a feel thing, but. Oops. Okay, so this one would be, and we don't even have to, you tell me if you want to finish this, but we could just say u equals 16 minus x cubed, and that's going to be a good choice, because then du becomes
-3x squared dx.
and that's pretty good, because there's an x squared dx right there. Does that make sense? So that's going to work well. Do you want to finish that, or just want to practice picking the u?
Yeah.
Want to finish it? Okay. So what's this going to become down here then? Tell me what's this 16 minus x cubed to the 2 going to become? Okay, so that's going to become a u to the 2 on the bottom, which is a u to the -2, right? And then what is the x squared dx in terms of du's? Yeah, okay, so we'll negative 1/3 u up front. And now we've got a simple power rule integral, right? So what is the integral of u to the negative 2 du? Good. Okay, add 1, u to the negative 1 over negative 1, so or times negative 1, same thing, right? So that's gonna change the sign of this thing. So we're gonna get 1 over u to the negative 1, times negative 1 makes that a positive out front. So I can just call that 1 over 3u if I wanted, right? Or 1/3 times 1 over u plus c. Does that make sense? Okay. Reverse the substitution, and I get 1 over 3 times the quantity 16 minus x cubed plus c. Okay. Study that integral for a second. Where are we gonna have a rapid reminder? I'll leave it first then. Any thinking on that? Is this one where we want to pick a u?
And probably the square root of
Square root of t for our u?
t is u.
T is u? If I make, but now think, if I just let t equal u, all I'm doing is I'm just changing those to u's. I get the same problem I started with. If I pick the square root of t for my u, then that's going to actually work well for my du, right? But does that help me with the numerator very much? Not really. I mean, I'm not saying it wouldn't work, but ask yourself here, just because we're studying u-substitutions, you're not going to have to force it on every problem. Is that one you even need a u-substitution for? Now, I'm dividing everything by t, but I've got one factor in the denominator, t to the 1/2, right? Can I just split that into separate fractions? Right? That's not a big deal, really, right? I don't need a u-substitution there at all. If I look at this integrand, I could make that, what is t to the 1 divided by t to the 1/2? What is t to the 1 divided by t to the 1/2? T to the 1/2, right? So that first term just becomes t to the 1/2. What's 2t squared over t to the 1/2? Good, 2t to the 3/2. That's no big deal. That's just power rule stuff, right? Just integrate term by term. 2 iterations of the power rule. And we don't have to do anything special with that. Right? We agree? Okay. So we didn't even need to use it on that one. Okay, how about oops. Stare at that for a second.
Square x is equal to 10.
Not equal to.
No, derivative of it?
Okay, yeah, that's a derivative though, right?
So you put u.
So there's one of those you're kind of looking for u's and for du's, right? So when you see, if you think about your trig derivatives, you know that secant squared is the answer to one of the trig derivatives, right? The derivative of tangent is secant squared. So that secant squared pops out as much, if not more, than maybe what the u would be here. I don't know. I mean, the u might be obvious to you also. There's a composition there, though, in one spot, isn't there? We've got a square root of a tangent, and so that's a good candidate for u because I have a function of an internal function, right? So what do you think? What's good u? Tan x, yeah. Right? If I let u equal tangent x, then du is just secant squared x, right? Dx. So there's my du, and this just becomes, it ends up being pretty easy. This is the square root of u, so u to the 1/2 du, right? Okay. How about, let's do a definite integral one too. Those are actually easier, but we haven't done as many of those. It's been a little while. So what about something like this? Oh, here's a good one. Oh, yeah. So great. There's a good one. Oh, there's a doozy. I like that one. That was a little trickier. You got any ideas for a good choice of u there? How about that? And what's your reasoning for that? Okay, so that's not a bad idea, right? We've got this 1 plus, we've got a quantity to a power. It sure be easier if that were one variable to a power, right?
Yeah.
So it's a good choice. Yeah, let's try that. So if u equals 1 plus square root of x, what's that going to make du? Remember, x to the square root of x is x to the 1/2. 1/2 x to the minus 1/2 dx, which we could rewrite if we want to as x to the minus 1/2 is what? Okay, yeah, square root on the bottom. So that would just look like dx over 2 times the square root of x. Well, look what we have here. We have a dx over the square root of x, so we have this stuff right there in our integral, right? And this is a good substitution up here. So what does this end up looking like when we make our substitution? So this is just a, what? 1 over u squared, which if we write that as a negative power, just a u to the minus 2. And then what is this dx over radical x? 2 times du. Okay, so we get 2 times du. But we got a definite integral here. So remind me, what do we want to do with this? Now we could get the answer, reverse the substitution, and then evaluate it from x equals 1 to x equals 9. And there's a real temptation, I think, among calculus students to say, wow, I know how to do that, let's just do that. It's something I'm familiar with. Don't fall into that trap. You see, this is really simple. Right? You don't, it's something, it's one additional new step, I suppose. But it's way easier, there's much less chance of making an error.
Take the x's and the integral and just plug it into the u.
Yeah, good. Okay, we're just going to convert the x's to u's based on our u substitution, right? So we just ask ourselves, when x equals 1, u equals what? 2, right? 1 plus the square root of 1 is just 2, right? Everybody see that? How about this now? When x equals 9, u equals 4. Like that. And we end up with, that's a pretty easy integral to do. What's the antiderivative? We've done it already today. The integral of u to the minus 2 is?
That's u.
Okay, 1 over u to the negative, right? U to the negative 1 over negative 1. So I put the negative out front.
Yeah.
So I'm going to get negative 2 over u, right? From 2 to 4. Okay, so that's just, if I evaluate that at 2, I'm getting what? Negative 1 minus, if I evaluate that at 4, I'm getting, what do I get? Negative 1/2. So plus 1/2. What's negative 1 plus 1/2? Done. Right? Make sense? Yeah. Okay. Now, what's really pretty interesting about, and this is, just gotta show you this. This is really cool. If we graph those two things, come on. Now check this out. This is really a cool deal. I always think this is.
Do you do the
Question?
you do the plug in the bottom number first?
Yeah, right. You evaluate it. Right. It's the value at B minus the value at A. Did I mess that up? Oh, did I do it backwards? Oh, I think I did. You're right. I think I did it backwards. I plugged in the bottom one first. Whoops. So let me. Why I did that? That's pretty stupid. So this should have been other way around, right? This should have been. It's going to give us opposite sign. So it's the value. It's the area function at B minus the area function at A. So if I put the 4 in, that's giving me a negative 1/2 minus negative 1. So it should have been positive 1/2. Sorry about that. Yeah, good thing you cut that. Okay. All right. So now let's look at these two areas. This is really interesting. So let's graph this first function from 1 to 9. It's going to look totally different than the second function. It's amazing that this works the way it does, but this is kind of the beauty of math. So if I graph, what's that going to be? 1 over the quantity, square root of x, times the quantity, 1 plus square root of x, squared. Okay. Let's graph that from, how about from 0 to 10? And I guess I don't maybe need to graph from 0 to 10. That was a bad idea. Let me graph it from 1 to 10. Okay, much better. And
Okay, so let's calculate an area from 1 to 9. So 1. Oh shoot! I double clicked. I got so excited. So excited about this that I just double clicked. Okay, there it is. Right? So it gives us 0.5, right? That's what we knew. That's what we got. 0.5. Now, let's go back and let's graph on the same window. Let's graph this guy. So we'll graph from 2 divided by x squared, right? Well, let's call that an x again, obviously. 2 divided by x squared. Okay. And we'll do that from 2 to 4. Okay. Is that no? I'm just graphing the area under that function right there. Right. So it's the integral of 2. When we made our u substitution, this became the 2 times the integral of u to the negative 2. Right. So, right, that's the same as if I could put the 2 inside there. That's the area under 2 divided by u squared. Right. We'll call it x. Okay, and I need, what's going to be the biggest value there? I guess I better go up to like 1, huh? Let's see, I'll do this. What if I go, I think I can just go 0.5, or 0.6. Oops. Okay. There's our first function. There's our second function. Totally different looking, right? Same area, yeah. If I add up the area under that second one, after we've made that substitution, what am I doing? Jeez. I know. Jeez. How did I get this job? 2, 4. Oops.
It's so much higher, but it's so much.
Yeah, well, you get the idea. I won't show you the pretty picture, but isn't that interesting? And so, think what that's done, because this is a good, you'll think back on this. If you guys continue on in math and go a long ways, what we've done there is we've traded area spaces, and it's had some physical manifestation on what that thing looks like. It looks like what we've done to our new world, our new two-dimensional world, is we've somehow taken like the vertical dimension and stretched it up, and the horizontal dimension and squashed it a little bit. But the area went with them, right? And things have been kind of, we slid it around a little bit too. But that's really interesting. We literally traded one two-dimensional space for a more advantageous two-dimensional space to add up an area. Did the work, and instead of going back, we just said, well, we're just getting a number anyway. That's really cool. Stuff like that in math, that's one of the greatest tricks in math that you can do at all levels. When people do this, the smartest people in the world that are doing string theory stuff, they do the same thing. The very same thing. They start with one really complicated space. It might have 10 dimensions instead of 2, like a Calabi-Yau space, and then they bunch this thing up and then do some topological transformations, and they go to a different kind of a vector space, and where they can do the calculations, and they transfer back to the first one, and they can see what that means in terms of how gravity's at. I mean, it's really, that's how people do stuff, though. That's really, I just think that's so cool. Okay. Anyway, but I digress. Okay. All right, so time for maybe one more. At least we can pick a u substitution. What would we do? We won't be able to finish this, but tell me what would be an appropriate u substitution for, I don't know, for this guy. How about? Think about that for a second. See if you can pick a good u. What are you thinking? Cosine squared x? Okay, let's try that. If I pick u equals cosine squared x. Oh, just cosine x. Good idea. Yeah, just cosine x. Good. That's going to work, isn't it? If we pick cosine x, then, whoops, then du is just going to be minus sine x dx. Well, there's a sine x dx, right? And there's a cosine to the minus 2. Great, that works. Everybody see that? Okay, that's good. One last one. Let's sneak in one more. What about this? What if we had, let me make one up. Oh, here's a good one. This is a good one. This is a tricky one. Hardest one yet. Can you see there? Actually, what I want to do is make that secant cubed. There. Now it's better. That's a tricky one. Can you see? The 1 minus x obviously is going to get absorbed into our u-substitution. But in terms of those trig functions, can you see a u and a du relationship? Think trig functions and their derivatives. Is there one that might fit? Having a secant and a tangent? Tangent would be secant squared. That doesn't quite fit though, does it? Because if I pick tangent for my u, I got secant squared, but there's still a secant hanging out there that didn't get included. Okay, now there's an idea though. The derivative of secant is secant times tangent, right? Okay, so I gotta hustle. But what if I said u equals secant of 1 minus x? Then du is secant of 1 minus x, tangent of 1 minus x, times derivative of what's inside, so it'd be a negative dx. Wasn't that just a u squared times a du, right? It's just because that's the same thing as saying secant squared times secant times tangent, right? You see that? Ooh, I wish I had just one more minute on that one.
Oh no.